Okay, so welcome everybody. It's for me a pleasure to introduce you, Professor Oda Seifer from TU Dresden, Technische University Dresden. I was working with him as a postdoc, my first postdoc, when I was much younger than now. Okay, and since then we have been meeting in conference now and then, and always we have proposed to invite him to come here. Lately we tried with the corona and so on, and it was unsuccessful. So I hope this time he managed to arrive to San Sebastian, and we can have some interesting ideas to discuss in the future. Anyhow, he will be here till tomorrow. If in any case any of you want to discuss something with him, it will be a pleasure to make some slot for you to discuss with you. So please welcome, and the floor is yours.
So thank you, Andres, first for the nice introduction and also for the invitation, of course. And as Andres already mentioned, we know already for almost 30 years when he was as a postdoc in my group in Dresden. Then later we met 15 years ago and had some small projects together, and I'm happy that I had again the chance to come here to this really nice place in San Sebastian. Okay, I will give a bit an overview about things we have been working and also give a certain outlook. So I will not go into technical details of the things. If you have questions, we can discuss afterwards. Okay, the title of the talk is Bridging Scales in Material Simulations, and that's connected to the question quantum versus classical simulations. And well, there is, of course, during the past 50 years, strong progress in quantum simulation with the development of the density functional theory, also to some extent with Hartree-Fock and configuration interaction schemes in coming more from the quantum chemistry side. And that, of course, was closely related with the development of the computational power, which has been the background of this, was the basis of this development, of this progress. Okay, but then there is also a progress in approximate methods. Though we have this vast development of computational power, you always reach a certain level, a certain size of the system where you say, oh, the computational power is not sufficient. And so you have to switch to approximate methods, not full first principle, approximate methods. And that has been done already in the 60s when the computational power was quite small in quantum chemistry, especially with the so-called CNDO, INDO, PM3, and so on, and more in the physics part with the tight binding methods. And then there is also a combination of tight binding and density functional theory with this density functional based tight binding methods, DFDP, which we applied a lot and also contributed to the development. And now it is possible to treat systems with, say, 50,000 electrons, quantum mechanically. This is now feasible with approximate methods, and maybe in 10 years also with the full ab initio methods. Now, illustrating a bit this bridging scale problem. So here is shown the length scale. And here is if you do, for example, if you want to study dynamical processes, so you have a time window from femtoseconds up to nanoseconds and to even longer times. And of course, when you go to smaller and smaller systems, you can use methods which are very accurate. So you have a high degree of predictivity, very accurate, high degree of predictivity. They are known from the basic systems, many monoplacid perturbation theory, multi-reference CI, and so on. And then that happened already in the 70s. Then there came out the development mainly of the density functional theory-based methods, which made a strong progress. And you could, at that time, and even nowadays, can go to larger systems. A bit losing, maybe you lose a bit of productivity character compared to this, but you can go to now, I have sketched now is a molecular system. You can go to larger systems. You can go in the time scale, into the picoseconds time scale. But then if you want to go to even more complex systems, going along here to larger length in the length scale, then you have here this approximate DFT schemes, which I mentioned, or semi-empirical quantum mechanical methods. But still, for many purposes, practical questions, you could say, well, this is too small or too short in the time scales. And then you have to go to molecular mechanics, force fields, like, for example, charm, just as an example of one of these force fields. Empirical force fields, forgetting about quantum mechanics. And, well, still, to even larger systems, you have to go to continuum models, continuum electrostatics. This is so the bridging scale problem from very accurate for small systems to large systems in a long time scale for very large systems. Often practical questions are connected with this. And then you are living in between here, and depending on the question you ask, you have to decide on which level of scheme which scheme you will apply. Okay, and then coming, say a few words more to the scaling properties and problem. Density functional theory has a problem since the size scaling is n to the power of 3. So it's far beyond a linear scaling. So with the increasing size, you have to the n to the power of 3. And even the development of computational power is not like n to the power of 3. It's more, let's say, linear. So you always easily face the problem of the size you can handle. Of course, density functional theory is behaving much better than Hartree-Fock, which scales roughly like n to the power of 4, or even when you go to even more accurate methods to configuration interaction, then it's scaling n to the power of 6. Of course, there is also some progress, which I will not discuss here, with some using some screening arguments to improve a bit the scaling behavior. Does this mean screening decreases a bit the scaling problem to smaller scaling? And connected with this, that would be also here nice, there was always the need to develop so-called order n methods, methods which develop not like n to the power of 3, which develop like linear with n. These things has been studied in the last 50 years intensively, but I don't think that there is really that method which is scaling like order n. And what does it mean, order n? You have things here I have sketched as a function of size. So a DFT method scaling like n to the power of 3. And linear scaling methods, you have to consider also what is the slope of order n scaling. So when you have a bad slope, then you can go to system size where even an n to the power of 3 method like DFT is faster than order n methods. No? But anyway, there will always be this break even point when the linear scaling comes through. And how this can be realized by order n, and a lot has been done with parallelization. And nowadays, if you buy even a small laptop, you get already a few core system, and you can go to larger systems, computational larger systems with many nodes. And so you can easily parallelize the things, but not everything can be parallelized. So, for example, parallelization means in the quantum system, you can distribute your Hamiltonian matrix or the overlap matrix to groups of atoms, to several different nodes. And in this way, you can really speed up the things considerably. But for the quantum methods you have at the end, if you have distributed or set up the Hamiltonian and the overlap matrix, you have to solve an eigenvalue problem. That's at least mostly the problem you have to solve. And that is difficult to parallelize the eigenvalue solving problem. But doing all the things, you can go now to, in the nanosecond simulation time, and up to 100,000 atoms using this parallelization and order n. Just to briefly mention, we did also develop something in this thing which is not linear scaling, but at least n log n scaling, like a Carr-Parnello method. And as an example, I show you here just a thing which we studied years ago, this immogolite, which is the only tube which occurs in nature. And when you start with a planar structure, you see this structure is spontaneously bending, and that could be done applying with such methods. So we started with a planar structure, left the system run, and then you get a bending structure, which illustrates, okay, for this special structure of magnesium silicates, you get a spontaneous bending, and that makes clear that these tubular can even appear in nature as a tubular structure, immogolite, as an example. Okay. Now, another things where we did many studies was connected with mechanical properties of a certain nanotubes, inorganic nanotubes, molybdenum disulfide-based nanotubes. There's a group in Israel led by Reshef Tenne, who has done many investigations on such inorganic nanotubes. And we performed also many calculations on this, and they are much larger the structures in carbon nanotubes, then you need more efficient methods. And we could calculate with these methods, with density functional based tight binding methods, for example, mechanical properties like the Young modulus of these tubes as a function of the radius. And here, this is also the characterization of the tubes are this armchair and zigzag tubes, and they increase Young's modulus with size. And this fits pretty well to the experimental data. The experiments were mainly done on tungsten disulfide nanotubes, and in bulk, there's a factor of 0.6, and they measured about 107 gigapascal, and that fits quite well to our calculations. So one could say we can really predict mechanical properties of such tubular structures. And then in the group of Reshef Tenne, they have performed interesting experiments. They performed direct tensile tests of individual MOS2 or tungsten disulfide nanotubes. This was mainly this group of Reshef Tenne and others. And what they did, they put between two cantilevers a single tube, and then they applied a force, stretched it until the breaking point. And now the question was, Reshef asked us, could you perform for such single nanotube a calculation where one can see this breaking process? And that we tried. So we made a setup. This is now this tubular structure. We applied an axial strain, and we performed molecular dynamics simulation with a quantum-based, density functional-based tight binding method for a certain tube at a certain temperature. And so we, oops, sorry, that was so wrong. I have to, where's the arrow? Yeah. Okay. Now, this is a simulation. You stretch the tube, the atoms are moving, and at a certain point, you will see the tube breaks here. So you get an atomistic level picture how this breaking process takes part. And this is now the process on an illustrated on an energetic scale. So here is delta L over L, so stretch over the length. And here's the energy as a function of the stretching. So you increase, you have an elastic behavior until a certain point, and this is a breaking point. So this is it. You have the intact tube, and here it is broken, is here. And so you get, you get here at about between 15 and 20% is that you can really stretch such tube. And that also fits roughly with the experimental data, but with this, we can get really an atomistic view on such process, of a really mechanical process, but done with a quantum mechanical calculation, certainly with some approximations, but this can be done. This is just an example. Another thing which is also related to mechanical things, when MOS2, you know, it is a layered compound, and in the group of Andras Kish at EPFL in Lausanne, they performed such experiments. They put a single layer of MOS2 over such plate, and then with the cantilever, they pushed on the surface. And the question is, again, what happens? How is the mechanical response of the system? They performed the experiment, and we tried to simulate this. So we selected a certain circular plate of this. We fixed at the boundaries, and then we simulated a kind of this cantilever, and then we pushed on this layer. And again, using this method, DFDB, with molecular dynamics, what is the response of the system when you push it? And again, now we get again a video. Of course, you have this vibrating of the layer, and now we push on top with the cantilever and look what is happening with this structure. You see it's bending, again, first in elastic bending, and at a certain point, as you will see, we destroy the structure here. We destroy the structure. Yeah, I don't want to go into the details, simulation parameters. Again, we did molecular dynamics within the Bohm-Oppenheimer approach, quantum mechanically with this density functional base type binding, a certain temperature, some control of the equilibrium, and then these are just data of the simulation. And then we could compare this also with the classical elasticity theory. Again, I also won't discuss this here in detail. We can, so to say, then really can make the bridge between the atomistic scale on a quantum level to classical mechanics, engineering mechanics. Yeah, and that is compared also with some experimental data, deflection of the membrane with results of the simulation. Yeah, and that is again, here you have similar to this stretching of the tube, you have here this elastic behavior, this plate reacts elastically, and here you get in non-reversible deformation, you destroy the thing, have plastic deformations in the system. Yeah, okay, these are just two examples we studied. Of course, we have done many examples, and not only we, many groups in the world did such studies. And as I said, nowadays it is possible to study systems with, let's say, 50,000 electrons quantum mechanically. And this is already close to that you can approach to the classical mechanics to investigate really real systems. But nevertheless, you might ask the question, is this really meaningful for, let's say, real materials or biochemistry, where almost no direct quantum effects occur? Since when you do mechanics, when you stretch a tube, you push on with a cantilever on a membrane, or you want to see some processes in the biochemistry, you do not see really quantum effects. They're not visible, at least not to me, and maybe also if you have another opinion, you can tell me. Yeah. And this is due to the effect we are talking about 300 Kelvin, room temperature. Of course, you see quantum effects when you go down to close to T = 0. Then you see plenty of quantum effects. You see also quantum effects at room temperature, but not in such, let's say, mechanical processes. And you have there an environment, the heat bath, which is related to this temperature. Yeah, and then you might ask the question, is this really meaningful? And this is again bridging the scale problem. You have a yes or no. You say, okay, when you have quantum effects, then of course you have to apply quantum mechanics. Otherwise, you do not get the right answer. On the other hand, you have classical physics. And the problem is there's no smooth transition between quantum mechanics and classical physics. It's not that you have, like if in the relativity theory, you can just tune the velocity of light, and then you can smoothly go from the non-relativistic to the relativistic behavior. This is not really possible for quantum mechanics. You have to say yes or no. And yeah, and then you have this problem of the quartz-grain simulation, atomistic quantum, or on the other hand, when you forget about the quantum things, you have to go to empirical force fields and applying molecular mechanics. But the important thing is empirical force fields. In the quantum simulations I have shown, you can say, well, this is not empirical. Well, there are some technical parameters. It's not, doesn't fall from the sky or so. But you start really from basic physics and you perform the simulation with some approximations. But fundamentally, you are on the quantum side. You do not, the forces you need for the simulation I have shown for the stretching of the tube or bending the layers, they are not empirically determined. They are calculated in principle, solving Schrödinger equation, in principle, yeah, forgetting about details. If you want to do it in a molecular mechanics, then you have empirical force fields. You have to fit something. You have to test it on something and compare forces between the atoms and compare them with the results you get in the simulation. This is empirical. That's, of course, a bit a disadvantage. Or even in the continuum things, and you have finite elements. I will not discuss this further. But the main thing is quantum versus classical physics. Yeah, and of course, there have been in the past developed such combined quantum mechanically molecular mechanics methods, which then allows really simulation of large systems like biomolecular systems, like here's this DNA chains, and here's some active biomolecule in between. And then they said, people do this, they handle this part here quantum mechanically, but embed this into systems which are treated with molecular mechanics with empirical force fields. Of course, in the field of biochemistry, you have the advantage that these are not exotic systems. These are organic molecules where you can make test calculations with high-level accuracy and then derive from their force fields. And yeah, of course, then the problem is still how to treat chemical reactions or excited state properties, spectroscopy. Well, this is important when you look for biomolecules more as an analytic tool. It's not so much important for how is the process going on. I mean, that is, excited state may play a role that you have, for example, photochemical reactions or something like that. But in biomolecular system, it is in many cases quite easy that you can separate a quantum mechanically treated system, and that is separated to an environment. And the quantum things are happening herein, and it's just you study the influence by the environment non-quantum mechanically and apply quantum mechanics only locally. That is an advantage in many biochemistry things. It is in material science much more difficult to find out this proper limit, what you say, cut out this part which you treat quantum mechanically in an environment which is treated classically. That is, in these cases, much more difficult. In biochemistry, it's more easy, and therefore Dutch method has been mainly developed and are very successful in biochemistry. When you go to, let's say, material science or other solutions, could be DFT a solution, go to really macroscopic systems. There were several attempts in the past already applying Thomas Fermi or Kim Gordon methods, and derived from their so-called orbital free density functional theory. That is, especially Emily Carter did a lot of work already some years ago, where you can go to practically large system, infinity systems, where you, to some extent, keep quantum mechanics. I can discuss whether this is really quantum mechanics or not, but so one. But this may be a way to bridge this gap between classical force fields and quantum mechanical stuff. But most of these things, as I mentioned already, they are empirical and they are cannot be derived from first principles. From a physicist's point of view, you want to have always the things from first principles. Engineers see this clearly from the opposite side. I don't know. I don't want, what does it care me whether it's from first principles or not? It has to work. That's our different points of view. Nevertheless, there are efficient quantum mechanical methods. And as I mentioned already, there is a big success with empirical force fields. And I think that progress of this empirical force fields will be pushed also by machine learning things, since machine learning and empirical force fields fitting can be really nicely combined. It is much more difficult to apply machine learning for quantum mechanical based methods. But for improving such empirical force fields, machine learning is certainly a useful tool. And this, I think, will push these empirical force fields in the next years, I think, strongly. And then, of course, it is often the case that engineering point describe macroscopic properties by atomistic simulations. It is nice to have from a physicist's point of view, but sometimes from the engineering point of view, who cares? No? Okay, but I come back now to this question. I repeat, is this really meaningful to do such large systems using quantum mechanical methods for real materials or biochemistry where almost no direct, I call it direct quantum effects occur? That it's, you can say you need quantum mechanics to describe the interactions between the atoms on a first principle level. But you do not see directly quantum effects like, as I said, for example, superconductivity also, where it's clearly a visible, in quotation marks, quantum effect. In this, what I mentioned already, and our systems we treat are open systems, since they are in a heat bath, in the environment, it's very difficult to make an experiment in a completely isolated system. There are always environment plays a role. There are open system. And there's a process which destroys the quantum mechanics, and this is decoherence. And there's a physicist from Vienna that wieso sieht die Welt so klassisch aus? It's German, he said. In English, it means, why does the world look so classic? I mean, why wasn't quantum mechanics observed much earlier than around 1900? Well, the world looks classic. Yeah. And why is the quantum world so invisible? For example, for chemists, a chemist with a test tube would say, well, where's the quantum mechanics here? I don't see the quantum mechanics. No? And the reason is the quantum decoherence. A German guy who died already some years ago, Dietrich C., had contributed strongly to the development of this quantum decoherence. This is, for example, one of the first papers. And and the point is that is often overlooked. The time for decoherence, when you have a system, which is, you prepare a quantum state, how long it will take that the quantum coherence is gone, that is in a very short time scale. Typical decoherence times are in the order of 10 to the minus 12, 10 to the minus 15 systems. And that is a problem to prepare quantum systems. That's also, you could say it's also the problem why high TC superconductivity is not so easy. Since with the environment, you destroy quantum mechanically the things very easily. So when we apply quantum mechanical methods for real systems in an environment, so you deal with something which will not occur in reality. So, yeah. And that leads me to the outlook. The limits of the molecular model, you can say this. And as I mentioned, quantum mechanics for large systems, for 100,000s of atoms, yeah, it is a problem of the scaling. So it's a technical problem, but it is also a fundamental problem, since this is a consideration of the environment. Open quantum systems. There's often the question, how big is the largest system you can meaningfully deal with the Schrödinger equation? You could say, oh, you can deal with the whole universe. But in principle, yes. But what we deal with are finite systems, large, really tiny, small parts out of the universe in an environment. And for that, the Schrödinger equation is not valid. In principle, when you say it from the fundamental thing, if you have a small system, it couples with the environment, this leads to decoherence and destroys the quantum mechanics. So for a chemist in a test tube, when it will be impossible for him to prepare a quantum state in his test tube. And that needs, of course, also new models, concepts, ideas. You have to go away from Schrödinger equation, generalized master equations, von Neumann equation, and so on. On the way on that is already the application of path integral methods. Yeah. We have, for example, as an example, to learn a bit more about this decoherence, we have done the studies a few years ago. What is the role of this decoherence in very specific systems? As an example, it was more for me to learn the things a bit more. Okay, and with this, I want to close, and I thank you for your attention. Thank you very much.
So thank you very much for the overview of the methods. I'm going to the point of what we know now, use of the thing. There is any question in the audience? You want to comment? Okay. I have several, but one of mine is well, you were doing some of this, I will be more than on the models and I think this question of the open systems is very important, not only for, let's say, covering some properties, but also for this, or even going to very low scales, when you, not to very large scales, but very small scales already, all this kind of coherence or the coherence in these quantum states, magnetic states or spin states that you have and so on will be an issue to do how the systems couple, also how you engineer the systems with light or magnetic fields and so on will be a real problem there. And I think this is something really I would like to know more about this this open stuff, a little bit more about.
This point with this open system is really an issue, but I think one has to distinguish. When I say a large system, and I want to study, for example, time-dependent processes or every magnetic excitations, electronic excitations, and so on. And this, you say, I have to do quantum mechanics, and one has to consider this decoherence. I think when you really want to study the process, then it's really necessary to consider this decoherence. Otherwise, it is not really relevant. On the other hand, when we want to simulate materials where I think quantum effects really, for like cement or so, you will not see quantum effects. But there is more a practical question. Can you get transferable, reliable force fields? If this is possible, then you could say, I do not need quantum simulation. But if you want to look, for example, what are the optical properties, then there is not really a way to get rid of a quantum simulation. But a quantum, I wouldn't call it quantum simulation, I would call it quantum calculation, not a time-dependent simulation. It's a process and just the properties. And that is the question, how good are our empirical force fields? How can they compete with first principle-based, quantum mechanically based force fields? Then the advantage of this quantum mechanically based forces are they are in principle first principle. It's not, well, you may always argue there are technical parameters and approximations, but they come really from first principles. And that is a balance you have, and it is less critical connected to this problem, decoherence. Decoherence is you want to simulate a process for a large system, and then you really may ask the question, is it meaningful to do it quantum mechanically? Still, you can calculate the forces quantum mechanically, but for example, what we did also, the simulations, the time evolution, classically, on Oppenheimer molecular dynamics. We solve equations of motion, classical equation of motion, but calculates the forces quantum mechanically. That is again this question, if I would have forces, if God would provide me some good forces, formula for the forces, why I should do this complex calculation.
There it seems that the problem of the coherence goes beyond also having a simple path, no? To this kind of coupling to a path. They will be much different from that. There is no.
Yeah, I think that's a problem to describe a proper description of the path, and the coupling is also difficult. I have no general solution
to choose.
And all these decoherence models, I know, well, I'm not, what we tested, they are also, most of them are also more playing with a parameter instead of doing,
Any other comment? I have one concerning, yes, is a physics issue. It's about you saw the breaking of a molybdenum disulfide nanotube. It's always, the breaking is always like this, never goes like
that
it has some special, because
I think
it's a special direction, or it's like if I took like an NM nanotube, the braking will go in some sort of N0 direction, or is
Okay. There is a difference. I have not here some simulation. We did make, and many others made simulations with carbon nanotubes.
Yeah.
Carbon nanotubes behave a bit different.
that's
Since there you have this chain like, well, like when you have a chewing gum. Molybdenum disulfide, for us, it looks more that it cuts really. Then you don't have this in contrast to carbon.
You start to stretch it, and then you have defects that start to reconstruct it, and so on and so forth. You don't have the same mechanism for this in organic.
For me, it's different. Of course, you mentioned defects. We started with ideal MOS2 nanotubes. So role of defect is another story.
Yeah, because in carbon nanotubes, what's happening when you start to break, you start this stone waves reconstruction, and you have these 5 pentagons. The 5 pentagons start to separate it, and then start to be thinner, thinner, and thinner. But still, you found the structurally is still there.
Yeah, still you have, even we have a defect in carbon nanotubes. Then this is, of course, a nucleus for the breaking, but nevertheless, you have this general process, which I would call a chewing gum process. In MOS2, I think we have not studied the defects for stretching. Maybe I don't remember exactly. But nevertheless, I think this typical that it breaks at a certain circumvent is, for me, typical for this type of nanotubes.
And my last comment is a little bit these reacts. You see that you put the reacts that will be like the ideal. It will solve everything.
No,
I just to do any other kind of calculations.
I put this just as an example.
All the reacts already, we know it has, in certain occasions, has some problems even.
I put this only as an example. I mean, that is a problem of all these force fields. The transferability. I mean, how you make it for a certain system, can you transfer it to another system?
And things like that didn't work very well.
But as I said, I mean, there will, in near future, that's my expectation, due to this machine learning everywhere, and machine learning can nicely combined with further development of force field and less with the development of quantum mechanical methods. And so maybe there will be a more push to this empirical force fields. Especially engineers are interested in results. And they don't ask, now, where did you take the forces? If they fit to the measurement, it's okay.
It's fine. Okay. We have no work. Okay, yes, please.
Just a curiosity, but the simulations that you showed, do you know of any that have been done with classical molecular dynamics?
Yes.
Like the breaking of.
As I said, we calculated the forces quantum mechanically, but then performed the molecular dynamics within the Oppenheimer approximation. So we solved classical equations of motion.
But with the forces?
With the forces from the quantum calculation. So it's not a full quantum simulation, yeah.
Okay, and something fully classical? Like fully, like with charm, for instance?
No, that would be fully classical when you calculate.
Yes, but this, do you know of any simulation of like, this of stretching, fully classical?
You ask whether there are such? Not for
like if you know of any and how it
goes. For carbon, certainly, but for MOS2, I'm not aware, since it is much more difficult to get a good force field for MOS2 than for carbon.
True.
If there is any more questions, so then let's thank the speaker again. Tomorrow, if anyone of you wants to talk to him, it's welcome. Okay, thank you very much.